All right. Well, I think because we do have a nice amount of individuals who have come in, I am happy to start this panel session. And Pierre Gentin, if you would be willing to lead the introductions.
Uh, Thanks a lot, Geneva, and welcome everyone. So it's a real pleasure today to start the first inaugural LEAP Wallerstein panel series on AI and extreme weather preparedness. So I'm Pierre Gentin. I'm leading the Science and Technology Center, which is called LEAP, and that stands for Learning the Earth with Artificial Intelligence and Physics. And what we are trying to do is using AI and machine learning to try and improve the reliability, utility, and reach of climate projections, and especially with towards climate adaptation. And as part of our mission, we are really trying to develop what we call bidirectional knowledge transfer. So trying to provide science to a broad range of stakeholders, but also learning from people to see what are their needs. And that's very much aligned with this particular session that we are going to have today. And I would like to emphasize that this series has been made possible through the donation of David Wallerstein to LEAP, and that's actually supporting a lot of the work from Geneva List. And the goal of this panel series is really to explore how AI can be used to improve extreme weather preparedness across the pipeline. And that goes from early warning systems all the way to actually providing information to people. And I think it's very timely because climate change is really fueling a lot of the increase in extreme events, droughts and flooding events in particular. And we're really in the midst of also the AI revolutions. We want to see how AI could potentially help solve many of those issues related to climate change, especially related to extreme events. And really, AI presents a host of opportunities, especially in terms of overlapping between climate, environmental, and societal challenges, but could also be framed as a way to provide AI for good, in that particular case for that series that we are hosting here. And today we wanted to start the series with something very dear to my heart because I happened to be in Valencia this year when the major flooding happened last October, and I was very kindly hosted by Gustav Kemps-Weiss, one of the speakers today. And that was really heartbreaking to witness the impact of such a big event at scale, really wiping out a major part of the city. And that's something when you even know about it, I've been trained in hydrology myself, so you know about that, like textbook type, but just witnessing that and witnessing the impact of those extreme events is really heartbreaking. I just like to emphasize that with Gustav Kemps-Weiss, we are actually leading also a European Research Council synergy grant, which is called USmile, with our colleagues Veronika Eyring and Markus Reinstein. And that's also trying to use AI in terms of monitoring, but also in terms of better predicting the impact of climate change. So very aligned with what we are going to talk about today. And so without further ado, I'm going to be passing back the baton to Geneva. And Geneva is actually really leading this effort for this AI preparedness series. And thanks so much again. Welcome, everyone.
Thank you. So before we launch into the discussion today, I just want to give a little bit more background as to what we're hoping to build through this new online monthly series. So as Pierre mentioned, we want to create a space to address extreme weather preparedness gaps and learn from experiences of what has worked well and what could be improved, especially through the lens of AI solutions. And again, as Pierre mentioned, we really want to look at this holistically through the entire disaster management cycle. So from preparedness to mitigation, response, and recovery. So we'll be talking about AI and weather and climate forecasting. We'll also be looking into decision-making and policy frameworks, as well as communication and engagement to help us reach that last mile. And what I really want to emphasize for all of you here, and I'm so happy to see such a big turnout today, is that we want this to be more than just a panel series. We envision it going on for over a year. And alongside these monthly sessions, we are going to be creating kind of continuous knowledge outputs, what we glean from the panel discussions, and some meta-analyses to really capture the insights, and also to develop a community of practice surrounding these topics. So we have a place where we can continue to go and share ideas and coalesce and build this series forward. So please do continue to follow this series and opportunities for continued engagement. I'll provide a link and contact info at the end. And so to not delay any longer, the overview for today's session is going to be first a brief presentation by our panelists. They're going to provide an overview of the flood events, highlighting their research as it relates to the flooding in Valencia. And it will be followed with a moderated discussion and hoping that there is time for some audience Q&A. I also want to note that we are recording this session and we will be putting it on LEAP's YouTube page and sharing widely with our networks. And as well, we are using Zoom's AI companion feature to facilitate note-taking along with our research colleagues, but to also facilitate those knowledge products. So please be aware that whatever you say is being recorded through multiple different means. So now I have the pleasure to introduce our distinguished panelists. So to begin, we have Gustavo Campvay. He is a full professor of electrical engineering at the Universitat de Valencia, leading the image and signal processing group. He was an IEEE distinguished lecturer, and currently he is a European Laboratory for Learning Intelligence Systems Fellow and Program Coordinator for Machine Learning for Earth and Climate Science. Also, he recently published a paper in Nature Communications, which I will link to at the end of this talk, on AI for modeling and understanding extreme weather and climate events. So highly pertinent to our discussion today, and please do check it out. We're also joined by Ana Belén Ruescas, who is an associate professor in the Department of Geography at the Universitat de Valencia and is a specialist in remote sensing. She holds her PhD in physical geography and has extensive experience processing and analyzing Earth observations data in thermal and optical ranges, alongside coordinating and managing research projects. Dr. Ruescas has taught courses in physical geography, biogeography, hydrology, cartography, supervising many undergraduate and master's theses and PhDs in remote sensing applications. She is an active researcher within the university's Global Change Unit and ISP groups, integrating machine learning with Earth observation analysis. Dr. Felix Frances is a full professor at Polytechnic University of Valencia and vice president of the Spanish Water Technological Platform and associate editor of the Journal of Hydrology. He has participated in more than 150 R&D and I projects in hydrological engineering, being the author of more than 300 research publications. Lastly, it is worth mentioning that he has recently obtained the State of the Art of Civil Engineering Award from the American Society of Civil Engineers. It's quite impressive. And to introduce our final panelist is Professor Dr. Luis Gomez Jova, is a full professor at the Department of Electronics Engineering at the University of Valencia, Spain, and a researcher with the Image and Signal Processing Group at the Image Processing Laboratory. His research focuses on machine learning and image processing, particularly in the application domains of remote sensing, data analysis, and multispectral image processing. He conducts and supervises research on these topics within the framework of many international projects and is the author of more than 75 international journal papers. So thank you very much. We are really pleased to have you here. And I will launch right into the presentation. So allow me to please share my screen. Oh, pardon me. Landed just off. All right, without further ado, please go ahead, Gustavo.
Hi, everyone. Can you hear me well?
Yes.
Good. Well, good afternoon and good morning, everyone there. It's really a pleasure to accept this invitation to talk about this, especially on AI and preparedness, and in particular to this case that we suffered last month here in the Valencia flooding. I would like just to be very brief in my perspective here. Can you please next slide? Yes, and this is basically what we want to talk about today. I will very briefly go through the expected role of AI in early warning systems and preparedness, and what can be done and what it is actually currently done and what has not been done yet. And maybe next slide, please. Yes, so just let me begin by acknowledging the United Nations definition of what is an early warning system. And I highlighted in bold like the real important words there in the narrative, right? So we care about prediction, we care about disaster risk assessment, communication, and preparedness. And all this has to be integrated and be helpful for individuals, for community, for governments, right? And it says take timely action, right? Next slide, please. So taking anticipatory action basically is calling for early warning or early action. And this is important just not to save just time and dignity of people, and also because we want to inform decisions before the crisis strikes, right? So this is important in terms of, you know, saving money and saving lives as well. You can, yeah, next slide. Yes, thanks. So anticipatory is important because, okay, if you prepare, you save all these things. But if you do not prepare, I mean, the cost of the inaction is quite expensive. I mean, it's very high, right? So it is actually just looking at the World Monetary Fund. It's basically estimating something between the 16 and 22% of the GDP by the end of the century, the cost of this inaction, right? And this is quite a severe and important cost. Next, please. So let me just go very briefly about what is the integrated early warning system and where AI could actually contribute. These are called the 5 bridges of death. It is not because people is dying, but because in order to achieve an effective early warning, you have to cross all these bridges, right? And we start from observation. Please, next. Yes, there should be an animation. Okay. So in this case, in the first step, let's say in the observational and sensor technology is quite advanced these days, and AI and Earth observation through satellite and remote sensing imagery is actually advancing very much. But not only images from satellites or drones or airborne sensors, but also weather stations, praxis, hydrological monitoring stations, etc. So we are witnessing, like, you know, an explosion of data volume and variety. And now there is this, you know, this very nice possibility or opportunity of exploiting or harvesting the information in this huge amount of data. Next. So the second step is about the weather forecasting, right? And you can only have to look at what is happening at least in the scientific community. There's like every now and then you just blink and there is a new AI-based weather forecasting model in Science, in Nature, in many different important publications, and the field is actually advancing very much. So it can be actually called kind of an AI revolution of the weather forecasting. So there is this very nice possibility of running forecasting at a very, you know, an unprecedented accuracy, but also speed and affordability for local centers. And this opens like a wide range of possible applications almost to anyone. No? So we are talking more about democratization, right? So the impact of AI in this arena can be very high. Probably not now because it's still in its infancy, but, you know, in the future can go very well. Next, please. And now we are dancing in the chain, and I think this is one of the most important challenges that we are now suffering when we want to apply AI in this arena, which is about improving the hazard forecasting, but not only hazard, but in the next bridge, please, it's about the impact forecasting. And in these later stages, AI has not been still integrated in most of the early warning systems. So as you can see, if you look at all the bridges, the important thing is not only about the prediction. Prediction is just a tiny step. It's more about, you know, forecasting impacts, forecasting also, you know, and hazard forecasting. But also towards the end, we want to have like a, you know, consistent warning and also, of course, helping the decision, right? And this does not only involve computer scientists and experts or domain experts, but also you have to integrate a wide variety of data from socioeconomic data and economical modeling, also people working in communicational science and behavioral psychology, right? So to achieve basically, kind of an integrated evidence-based recommendation, right? So AI is still in its infancy, as I said. It is slowly being integrated in some systems here and there, but it is still not there, right? So with that, over to you, Anna. So maybe you can tell us in advance a bit what it is the case of Valencia flooding, and then you will try to summarize all this, or some of these points. Right?
Yeah, I will just summarize. If you could pass the slide. Yeah. In the case of this event, it was an extreme event, we have to say, but the meteorological forecast, I think it worked properly. The forecast was quite precise, I think, and the alert that the Spanish Meteorological Agency launched was on time. So even the University of Valencia with a orange alert, so it was not even the higher alert, already decided to cancel classes. And on the morning of the 29th of October, when the event started to happen, the IMET, the Meteorological Agency, already launched this red alert that is based on thresholds of precipitation by period of time. So when there is a lot of rainfall in a short period of time, the risk is extreme, and they launch this red alert. And that was done even using numerical models. No AI is still in this field, but the forecast was pretty good. And that is shown by the maps that you can see on the slide, and the pre and post event. And you can go to the next slide. And then we had a consequence of this high intensity precipitation and high concentration of rainfall in the upper part of the river basins. What it started this flash flood event that is quite usual, let's say, in these semi-arid environments like we have here, where the soils don't have the capacity to absorb too much water, and there arrives a moment when they saturate and it starts this runoff. There are also other problems, other issues that cause this big flash flood event, especially on the northern part in Cuenca del Pollo, because there were also some historical hydrological modifications of the channel that somehow could have been affecting to increase the risk and increase the flash flood that arrived to the rest of the basin, to the lower basin. We can talk about it later, maybe with Felix that comes after me. And yeah, I think that's all. I wanted to just to put people on the context of this high intensity rainfall in a few hours, and with this flash flood event with an irregular hydrological system. Yeah, well, that's the effect. I forgot I put this slide. Sorry. That's the effect of the events on the south of Valencia mainly. Yeah, as you see, streets full of mud and a lot of still water on the roads, etc. Yeah.
Okay, then it's my turn. It's difficult because for me, because every year I have a seminar of 10 hours about flood risk management. So to concentrate 5 minutes, I thought what can be the most important 4 ideas. So next slide. The first one for me, I think is that it must be clear the difference between 2 different elements. On one hand, on the right, the flood inundation area, the potential flooded inundation area, and on the other hand, the catchment. And it's important to distinguish because two reasons. The first one, the scale. The catchment is about in the order of square kilometers, hundreds or thousands. And on the other hand, the inundation area is 1 or 2 orders of magnitude smaller. We usually talk about hectares. So the scale is different. And the processes in the catchment, we have the precipitation, and we have the runoff production, and also we have the propagation through the catchment. Just upstream the inundation area, the yellow arrows or the different 7 small catchment going. Actually, this is an example of the upper part of the Pollo Creek inundation area with 7 different inputs, and in the inundation area is basically bidimensional, a 2D flow, water flow. Next slide. The second idea is to distinguish clearly the difference between the hazard and risk. The hazard is the combination of the frequency and magnitude of the events, in this case, the floods. But if there is no exposed human assets or vulnerable assets, there is no risk. Only in the case that we have exposed vulnerable land uses, then we can have risk exposed to hazard. Okay, and the risk can be measured in economical terms. One back.
Right.
In economical terms, or in affected population terms, or in cars waste up, destroy, whatever. But at the end will be in any unit, it will be the mean negative consequence, the annual mean negative consequences at each pixel or for the whole inundation area. And something important that was underlined in the European directive about flood risk management is that the objective must be the reduction of the risk, not the reduction only in the hazard by itself, not constructing dams or whatever. It is reducing the risk. Constructing dams, we reduce the hazard, or with afforestation, with green corridors, it's a reduction of the hazard. But with our early warning system, and as Gustavo explained before, we are reducing the risk, reducing the vulnerability. Or something very important in practice, with hazard mapping, we will reduce the future exposition of talking about land use planning. Next slide. So at the end, in this case, for hazard mapping, for hazard estimation mapping, we have a cascade of models. In the catchment on the left, we must have a meteorological model and a hydrological model to convert precipitation in runoff, and a statistic flood frequency analysis to estimate the frequency, the probability of things. And on the other hand, in the inundation area, you must have a very detailed, usually a very detailed hydraulic model, very detailed, including, because it's important in this case to know if one house can be flooded or not for different probability levels. And the important thing is that there is no one common model, because the numerical integration in time and space grid is different. In hydraulic modeling, it's very fine in time and space, and in the case can be wider. Next slide, and last one. And talking about flood forecasting, that's a different story. In flood forecasting, well, different. There are similarities, of course, but there are specific things. The first thing is that we must deal, yes or yes, with uncertainty. The source of uncertainty, the main source of uncertainty is the meteorological forecast. Another thing is that this uncertainty increases with the lead time, with the time in advance that you are producing the forecast. And the second thing, also interesting for AI, is that the computational time, especially the 2D hydraulic modeling, is so high as compared with the lead time, the usual lead times, reducing the warning period to make possible to deploy the emergency plan, which is important in case of emergency. That's all for my side now.
Luis.
Okay, thank you, Genevieve, for the nice introduction. And then also in this last part of the presentation that I tried to introduce is also that, okay, once you have the event, in addition of obviously before the event, you have to try to do this kind of forecasting and also to analyze the risk. You have also to monitor, once you have the event and you have the flooded area, you have also to monitor the impact of this flood. And when you want to monitor these events, obviously you want a continuous monitoring. You want that in principle they have to be global because not all the regions and all the nations, they have the same resources. And also you want to do this in an automatic way, trying to be the most objective as possible in any area in the Earth. So for this, it's true that Earth observation with all the remote sensing satellites that are observing the Earth in combination with artificial intelligence can be a perfect tool to do this kind of monitoring. Basically, we obtain a lot of images from for example, from ESA or NASA in a lot of different frequencies, because it's true that when you try to observe the flooded area, you can use a lot of different characteristics of the flooded area in the optical, in the visible, obviously, but also in a lot of different wavelengths in the spectrum, in the spectral domain, and also with radar images. But it's true that when you try to combine this with artificial intelligence, you need a lot of effort also to try to build these machine learning models with supervised data. So this implies also a lot of work building global training data sets that you can use to train the models with the objective of providing these accurate flood maps at the end. So next slide. So for example, in the case of Valencia, in the Valencia flash flooding, we obviously, the same day that we have this dramatic event, we start to look for all the resources that were available at this moment. We combine images from different satellites. For example, we get an image from Landsat just after the event, also from Sentinel-2 mission 2 days after the event. And then using also at the same time that we have optical images from Sentinel-2, we also collect radar images from Sentinel-1 covering the whole region affected. You can see in the images how the impact was really dramatic, because you can see all these brown areas where you have a lot of water combined with mud and affecting a very large region. And then we, with the models that we were developing in the last years, so it was a perfect combination that we were obviously researching on this field of using remote sensing data for flood detection. And we were in Valencia knowing perfectly all the region. We developed maps trying to support all the emergency systems and also to measure the impact. So you can see the large area that was affected by the floods. We also obviously try to distinguish between the areas affected by floods where you have, for example, agricultural areas and urban areas, and the other countryside areas that were not. This is related with this risk that we have mentioned. No? The hazard and the risk is different, completely different, depending on the area that was flooded. And how the Valencia city, the center of Valencia city, was not affected by the flood for different reasons. But the area that was in the south of Valencia, the area that was affected by the flood, was really large, and a lot of small towns were almost destroyed because the flood. So next slide. But it's true that for this flood monitoring after the events, we have a lot of challenges because not always we have the data that is required is available, and also the interpretation has to be very accurate and very, very fast. So the main problem, one of the main problems in these kind of events is the near real time that is required for supporting the emergency systems. And it's true that, as you have seen, the only images that we obtained were 1 day before, 1 day after, and 2 days after. So it's true that a lot of companies and also ESA and NASA, they are working on different satellite constellations to try to reduce the time and even build small satellites with the capability of changing the orbit to go directly to the locations where the images are required, to acquire the images in more or less hours instead of days of difference. Also, depending on the technology that you are using, the clouds are also a big problem if you are using optical data, optical instruments. But obviously, as I have mentioned, you can rely also on radar data. And also the spatial resolution is a problem because sometimes the available free satellites that you can use to support this global monitoring that is required, they don't provide the necessary spatial resolution for depending on which kind of surfaces you have. And we were working also applying artificial intelligence to enhance this spatial resolution in the main missions that are focused on this kind of Earth observation for emergency systems, in this case Sentinel-2 images. And finally, as you can see in this last image, is not the same the detection of water that we can do from space and with these satellites, that the impact of the flood event. For example, in this, just after 1 day, it's true that almost no water was present in the affected areas, in the urban areas that were most affected, but the damage was incredible. I mean, but obviously you even didn't see the water because it was full of mud, cars and destroyed buildings there. So it's true that we have to go also for this kind of multimodal approaches where we combine satellite data with all available measurements on ground. And this is critical for all this decision making for the national authorities, also the emergency units and all the people that has to take some decisions in very few hours, I would say. So that's critical.
Great. That was a fantastic overview. I hope everyone on this call feels as though they are able to understand the context that we're going into here for this discussion. And so I'm going to launch right into our first question here. So from your experience and based on your research, what were some of the critical gaps in disaster management during the floods? And what improvements do you think could have been made? Gustavo and Anna, we'll start with you.
Well, that's a very challenging question because, you know, there were so many failures, right? And then trying to organize everything in a sensible way, it is actually very complicated, but I will try my best. I think that there were, like, of course, failures, not only technical ones, right? Like the ones that, for example, Luis just mentioned. Let's say, or well, things would have gone better with better forecasting models, with better data, with better integration, maybe algorithms or methodologies that can ingest all kind of multimodal data. That there are technical challenges that, you know, if alleviated or resolved, would have improved the response much better, of course. But I would think of others more, let's say, not that technical. But for example, it was like a very delayed and ineffective warning dissemination, right? So the dissemination of the alerts and the alarms were completely a failure, and that was probably one of the main issues. Not, I mean, you cannot avoid the risk and the hazard, right? Anything, but you can avoid the disaster that followed up, right? So with so many deaths, etc. No? So that's nothing technical, or maybe yes, because AI now is being implemented. Maybe just looking at how other global best practices are now being implemented in Bangladesh, in Nepal, in other places. supposedly not that developed, but they are already integrating like automatic ways of formulating alerts and alarms and you know, and I think that we can learn from other places, right? That's one thing when it comes to the dissemination. There is also another thing, a particular thing that happened here in the region of Valencia, that I think that people is not really aware of the risk, right? There is like self-awareness is not something that I think that we have not been trained as a society, no? And that's something that we should work out much better in the future. So of course there is like this, you know, love and hate relationship between the society and let's say politicians, right? And then there's not such much trust, right? So even if they were delayed, imagine that they were well in time, people would not probably obey, right? The orders, let's say, of an alert, right? And of course, there are other issues that I think that have played a critical role here, which is about the let's say different levels of jurisdiction between the state and the regional governments, and also kind of a poor coordination of agencies. And yeah, and of course there are bureaucratic gaps that, of course, this is not our expertise, but probably they should kind of be addressed in the future. And of course, when we speak about more, let's say, technological failures, there were some failures, of course. You know, some sensors didn't work because of the flooding was so incredibly high, right? So huge that they were not really working. Also, the integration between systems is not something that we achieved in the last years. And yeah, I think the lack of preparedness, right? But I don't know, Anna. Yes, please. There are so many. I mean,
If I can add, I think especially from the two main agencies, the weather forecast and the hydrological agencies, I think in both cases the alerts were sent in time, so we have to separate about the alerts sent by these agencies and the warning that was sent by the the politicians in charge, let's say. So there was a big delay because there was a lack of communication or decision making that was not made properly. That was for me the main failure. So we know we cannot avoid these kind of events, and this is going to happen even more frequently with global warming and climate change. But we can alert the population, and we can also educate the population. We need also some pedagogy in making people aware that in some cases there are risks and they have to be prepared.
yes.
That's my point.
I think that's a really fascinating distinction between the alert and the warning and sort of the political coordination and jurisdictions. I would be curious to hear from Felix if you see this as having the role that the forecast and interpretations of forecasts transformed to warnings, if that might have played an issue, or how you see this challenge between a forecast-based alert and a warning. I'm curious to hear your thoughts.
Well, just to be positive before going with more negative things, we have a relatively good meteorological forecasting system, can be improved, of course, but it's good. The real-time monitoring system from the water authorities is, I think, is one of the best in the world at national level. We're not talking about experimental basing. We're talking about all the country. The interrogation time in 5 minutes is working pretty well. We spend a lot of money maintaining this system for the whole country, but there is no, in most of the water authorities, the Spanish water authorities, there is no any forecasting system. So what they can, in any case, what they can say is what is happening in the sensors. There is no way for them to extrapolate at present time using modeling, using AI, whatever, what is happening. And of course, they cannot forecast what's going to happen in the next hours or the next days. That's a lack. it's obvious that there was a problem with communication. The alert, the warning cannot be after the flood, of course. Must be. I thought that we have a very good civil protection system, but after this event, I must say that clearly can be improved, especially concerning communication. But I agree with Gustavo. There is no education and information. We have very detailed flood hazard maps, and no one knows that they exist, how to reach them. For the whole, for most of the urban areas in Spain. Planning is also an important thing. We had since the end of the last century a regional level planning regulation, land use planning regulation concerning inundation. We were pioneer, and I was involved in that project, the diagnosis of the hazard and risk at regional level. But there is no retroactive. It cannot be go to the past planning. Only it affects to only the plans approved that trying to be approved after 2003. So that's one thing that they are thinking to change, to act not only for the new plans, act also for the former plans that of course can be improved, because the exposition is increased exposition is the main source of increasing the risk.
And I think it's interesting that you have identified that you have incredibly strong forecasting, National Meteorological Agency, strong monitoring, and that data does exist, but that there are challenges in reaching it. And I think that if we were to extrapolate this to other parts of the world, you can only imagine the challenges that are faced when there are extreme events like this, when you don't already have those robust systems. But still, we have these threads coming through, issues of communication and data existing, but not being made aware of decision makers. I'd like to jump into the next question, where I'll start with Luis, if he's willing to respond. So in the presentations and lightly during this discussion, we talked about the potentials of AI-enhanced early warning systems. Luis, I'm wondering if you could elaborate on how AI can help to mitigate some of the impacts of extreme events. And in particular, what are the additional challenges that might arise when we're trying to literally bring AI-enhanced solutions, but to disaster managers and to local government decision makers? We've talked about collaboration and communication, but I'm curious if you can elaborate a little more. What's the opportunity, and then what do we really need to have this be practically implemented?
Okay, yes, because related to that is true that during all the presentation is true that I was thinking that since all we live in Valencia, I think that we were missing also one of the most important things, that was that 227 people dead during the event. I think that we have missed this number, and it's critical because now after the event we know that most of these people dead because the warning from all the emergency services, it fails. I mean, it was used, but this warning this alarm was given to all the population in the affected areas more or less 3 hours with 3 hours of delay. I mean, it was completely unuseful, and most of the people was already dead in this moment when the local government was submitting this kind of alarm. This is something that we know at this moment. And it's very related with, as you have mentioned, because obviously, independently of the particular failures that we have had, in this event, the contribution that we can have from this kind of machine learning or artificial or automatic systems for emergency and for early warning is because you have to combine a lot of information from different sensors, as Gustavo was mentioning. This is sometimes difficult even to interpret. I mean, because at this moment that we have, okay, we have all these instruments, but you have some alarms from the meteorological service. Then you have also some measurements of the basins, of the amount of water that you have at some point, but are completely unconnected with the other alarms. And they are provided to the emergency systems that not in all the moments they can calibrate perfectly well, which will be the impact.
And especially in real time, to do it in real time is, is impossible with classical tools.
I mean, it's possible if you coordinate very well and you use this kind of alert systems that have to integrate a lot of different data from different sources, but also have to be ready to provide this warning in a different way depending on the region, because the system can be the same. You can use, for example, the mobile phones or whatever, but has to be different depending on the region that you are located. And also the way to communicate with the people is critical, because what's a red or an orange or a yellow alarm? If you have not a clear indication of which is which are the actions that the people has to do at this moment, is useful completely. I mean, it's not useful if you don't know. Okay, you don't have to go to move your car because maybe it's that much because of the rain. That this was the case in Valencia. This was the case because usually you don't have this amount of rain. So most of the people is just that, okay, if it's raining a lot, I have to go to move the car from the flooded areas, because it's not going to be something really critical. So here was the opposite.
I feel like now
a lot of people dead because they were saying, okay, they have said that it's going to rain a lot, so I'm going to move the car.
And I feel like it's fascinating now that we're in this new normal of extreme events, that how are we going to communicate the new normal of disaster risk to people who have not yet, these are unprecedented. So I think that's a fascinating thing. And I'd like to I'm going to pose two questions to tie together to both Felix and Gustavo and Anna. We were talking about this trade-off of, you know, 3 hours, is that enough time? Not to mention the challenges with interpreting a warning. I'm wondering, Felix, if you can talk to me a little bit about this lead time versus accuracy, how we should think about uncertainty with regards to forecasts and what role AI might be able to play. And then I would like for Gustavo to kind of jump in and Anna to jump in at the end to talk about, you know, the trustworthiness and understandability of an AI solution that we know has inherent uncertainty, but in time-sensitive, literal life and death situations. What are some of these trade-offs, and what is a possibility for AI to step in and improve some of these gaps? So uncertainty, trustworthiness. Felix, we'll start with you.
Well, I believe in hybrid models, the combination of equations and AI. But in any case, but I'm sure that is the situation Luis was describing before, the combining different sources of information in real time. You have only minutes to take decision. Your prediction, in any case, will have uncertainty. Then the decision must deal with uncertainty. Choose the proper message. I think it's the right ecosystem for AI. Is the place where AI can be fast and give a solution. Of course, at the end, in any case, with AI, with deterministic modeling, there must be a human control of the final launching of the message. But choosing what to do with different sources of information, AI is clearly at this moment, we'll go for it. But not forgetting the deterministic modeling. It gives you the predictability part of the things.
Right. So hybrid approaches, being able to have multimodal, that's really one of AI's superpowers, but ultimately it resting with a human, a human agent making decision. Gustavo, I'd love to hear Yeah, about your thoughts.
I can add a bit on that. I think that, yes, I completely agree. This combination of hybrid or this combination of domain knowledge and machine learning that can give us like more trustworthiness on the what we are actually doing. I think that the key point here is uncertainty, but you can see that in all these bridges you will have uncertainty, and this uncertainty will propagate to the final decision making. And machine learning now, there's like a lot of investment and a lot of interest in quantifying and propagating uncertainties through the machine learning pipelines. I think that can and should be actually or even mandatory to have, like, you know, if you want to have a robust model that you can trust, you have at least to quantify how uncertainty it is interpreted.
Totally agree. Yeah, totally agree.
You have to be certain, right? And you have to also to be able to propagate such uncertainty through the models. And moreover, if you are coupling different models and interacting with different data sources, that they have different uncertainty levels and sources, right? That's with respect to the trustworthiness on the model. But we want more, and it is about interpreting what the model is actually doing, right? And then I think that there's this field of explainability or interpretability of machine learning models that is still, you know, it has a lot of challenges, but it is, I think, the way to go. You want to you know, to gain some confidence on the predictions, but also on what the internal mechanisms of the model is doing. No, something that we have when we do kind of parametric deterministic models, we can analyze that, but in the machine learning or AI arena, no? So, and there is an extra thing that actually Felix mentioned very briefly, which is about the computational cost of hydrological models or let's say, or these dynamical systems. And now I think AI can also provide good solutions, good surrogate models or emulators to these very complicated dynamical models. And at a fraction of the time, right? Once that it is trained, it can run very fast, no? But it would be useless if they are not like endorsed with this uncertainty quantification and kind of scrutiny, right? Or interpretability of what are internal mechanisms. So I would advocate for these three legs of the ML for the future of warning systems or whatever, no? Of course, you know, one can hypothesize on the last mile, right, of the communication of risk, right? And now with this, the advent of all these LLMs and chatbots that can create fantastic narratives, even controlled or constrained under whatever regulation or law, maybe that could give us like you know, something more automated, trustworthy, robust, and fast, right? Something that we have missed in this catastrophe here in Valencia.
Yeah, and also maybe just I think as reinforcing this idea that the society must also understand that AI can be great, but it also can, because of this uncertainty, could cause, for instance, false alarms. So, and we have to make people understand that this could happen and it's not bad. I mean, this is always better a false alarm than what happened 4 months ago. So I think there is I would like to stress this idea. We have to also make people aware of the risks and of the possible solutions in a better way that we have done until now.
Yeah, and I think as we get into this new normal, the concept of risk communications and also this capacity building for the public and for decision makers is going to be really critical, especially if we're bringing these AI tools and solutions to this space. And I really liked what you said about explainable AI. And as I think, you know, there's capacity building needed for the public. Can it be through improved risk communications with LLMs? And also this explainable AI. What is the future for decision makers and policy makers to understand that we have integration when we know this risk response is highly interdisciplinary. So I think we have our challenges cut out for us. I'd love to give the attendees just a couple of minutes to ask, I would say, maybe we can take 2 questions, but back to back, very short questions, and then the respondents, the panelists can try to respond in a couple of minutes. It'll be first come, first serve if there's anyone who wants to jump in here. Let me see, I can read this. We have one question. Is it possible for AI to help with the adaptation mitigation part of preparedness? For instance, could deviations from predicted drainage from an AI statistical model be used to quickly and specifically identify sewer drains are only operating at half capacity, or the grading of a specific road deviated water flow in a way that exacerbated flooding? Could AI be used for these types of solutions with regards to sewers, drains?
Well, in terms of computational times, yes, for sure.
Yeah.
We are thinking in something static, I understanding. For example, now we are in the challenge to renew the flood hazard map for the whole region of Valencia, at regional scale. We cannot do it using deterministic hydraulic models because there is no, well, let's jump to supercomputing, but there is no hydraulic models prepared for supercomputing. So one solution can be to use AI to speed up the results. It is.
And I know from a study that that's one of a big frontier, as well as AI sensors to monitor risk, monitor flooding of water systems, and also municipal drains and pipes, and for leaking and water waste. So I'm confident that it can be applied elsewhere.
For real time.
Okay, yeah, real time. Okay, so we've had 2 last questions, and maybe for 1 minute. I think the first is AI trained also using retrospective data sets. And then the last note, there were a lot of failures on the administrative level before and after. One beautiful thing is that the disaster brought forward was the resilience and willingness of the people to help each other. El pueblo salva el pueblo. Do you have ideas on how AI can potentially help people save people? All right, 1 minute to respond to retrospective data sets and el pueblo salva el pueblo.
Yeah, well, I have my personal opinion on the last one. It shouldn't be the case. Maybe it's beautiful and romantic to think that el pueblo salva al pueblo, but this shouldn't be the case. It should be the proper decision making done by the state and the administration that we selected as our rules, right? So, but in any case, I think it was just to finish with let's say in a positive manner. I think that it was like, a clear demonstration that the Valencian people was doing what the administrators were not doing, which was, working all together and helping each other. Yeah, that was definitely a positive message out of this. And probably, I don't know, if we learn something is that we need to decide better on what we want in the future, and to, we will continue helping each other. Yes. Even though that this shouldn't be the case, but yeah. Well, the previous question was something like, is AI trained also on retroactive data sets? Of course, and this I think is actually calling for this huge field in machine learning now, foundation models that can ingest all kind of wide variety of data and learn representations that can be then particularized for a particular, different scenarios, or slightly different, and fine-tuning to particular applications. So this is a very interesting question, and also, integrating not only weather and remote sensing, but also health and social economic data as well. Of course, that's the way to go, I think. Yeah.
All right, if there's not any other contributions, we are at time. I am going to just quickly share this to promote our upcoming talk. So as I mentioned, we're doing this monthly. Our future talks are going to look into early warning systems and anticipatory action around the globe. I'm really interested to see what is happening in other contexts. So you mentioned Bangladesh. I know there's really exciting work taking place all over the world. And we also want to look into decision-making and policy. And so, we're always going to have this thread about forecasting and modeling, especially coming from LEAP. But we realize there's this huge bridge of death, and there's a huge amount of potential that is both an AI solution and a people solution to improve the decision-making and policy around disasters. And this semester, we also want to put forth a case study on AI in wildfires and hurricanes, particularly in this region of the world, as that season is just a few months out. Again, we're building this series. We're eager to pull together relevant work from brilliant minds. And so if you have a topic of idea or speaker suggestions, I give you all permission to reach out to me directly. I've put my email in the chat and it's on the screen. It's gal2141@Columbia. Please do reach out to me if you have ideas. We'll continue to advertise the upcoming events, which can be found on LEAP's website, also copied, also on the shared screen. And yeah, we're excited to build this series together and build this community of practice together. And hopefully we're looking out to a horizon of more than a year to actually implement this. And I've also attached the Nature Communications paper, which is really an exceptional overview of AI for extreme event preparedness. So thank you all. This is a great turnout. Thanks for attending the inaugural session, and thanks to our wonderful panelists. This is incredibly stimulating dialogue.
Thanks for hosting.
Yeah.
Thank you for inviting us.
Yes.
Thank you.
Right.
Bye.
Have a lovely Friday.
Bye.
Bye.
Bye.